Navigation is not possible without knowing the time, in which direction, and at what speed a vessel is moving. Most radio navigation instruments and some Doppler sounders will compute the course and speed of a vessel over land, but a vessel of any size relies on the compass and the log to find the direction and speed through water. Logs measure the speed of the vessel. They can be divided into two categories. The first measures the speed through the water, and the second, the speed over the ground. Older logs work using a rotor or impeller, the speed of which is registered by the distance log and the speed log. These mechanical logs are subject to marine fouling and are not very reliable. Other logs measure the change of pressure in a tube, or the change in the electromagnetic field as water passes along the hull. The Doppler log measures the speed over the ground by measuring the Doppler effect from the return of a hydroacoustic signal. It doesn't give an accurate reading in deep water or very shallow water. It is essential to understand that if the Doppler log gives the speed over the ground, it is only to be used for navigating to a destination. Collision avoidance manoeuvres only refer to the speed through the water. The difference between the latter and speed over the ground is the combined effect of currents, tidal streams, wind speed, or possible instrument error. Ultimately, the navigator wants to know his speed made good, which is the speed toward a destination or waypoint in order to find his estimated time of arrival, or ETA. The magnetic compass is compulsory on any vessel. As it is prone to error due to the proximity of steel constructions and magnetic distortion, a deviation correction is used. Furthermore, its reading has to be corrected for magnetic variation, in order to find the true bearing or course relative to the geographical north. The magnetic compass is always placed outside steel constructions and is calibrated to compensate for local magnetic distortion. The gyrocompass is mechanically based on a gyroscope set to the true north. The latitude and the vessel's motion influence its initiation. Therefore, it has to be started in good time before the beginning of a journey and must not be stopped whilst underway. It is important to check the gyrocompass at the beginning of each watch and whenever speed has been changed. The returning echo is displayed on recording paper, on a monitor, or simply on a digital meter. The two former have the advantage of showing the signal strength and an indication of the nature of the seabed. A hard, rocky seabed will show as a bold line. A soft, muddy bottom will show as a diffuse line. On a monitor, different colours indicate the strength of the signal. Apart from the sea bottom, a recording echo sounder will also display echoes of schools of fish and even single large fish. Sometimes a false bottom echo appears. This is called a scattering layer, and it is the result of reflection between two layers of water with different density or temperature. This often happens at a river estuary, where a layer of fresh water lies on the top of denser, salty water. The first radio navigation aid was the radio direction finder. A land-based transmitter sends a Morse-coded radio signal on the long wave bands and on an onboard receiver, equipped with a directional antenna, takes a bearing on the signal. Two or more bearings on several radio beacons give a cocked hat position. Maritime radio beacons are often placed at lighthouse locations and work in sequence on the same frequency. This allows the navigator to take cross bearings without having to switch between frequencies. Aeronautical radio beacons near the coast can also be used for maritime navigation. Low-frequency radio beacon signals are bent by land masses, and therefore care should be taken when the signals received make a small angle with the coastline. The Decca system is British and covers most of Europe. It is based on the principle of hyperbolic lines of position. A master radio station sends a signal that is received by 2 or 3 slave stations. The slave stations then send a signal which, when received by the onboard radio instrument, is compared to the master signal, and the time difference is converted into 2 or 3 hyperbolic lines of position. The Lorentz system also uses hyperbolic lines of position, but it works in a different frequency range and has a larger range. The Lorentz is a United States Department of Defense system and covers the United States and part of Europe. The Omega system works on low-frequency signals from 5 worldwide transmitters. The system is based on range finding from signal time delay, being synchronized by an atomic clock. Omega is also maintained by the United States Department of Defense. The Transit satellite was the oldest satellite-based navigation system, but it is no longer in operation. Today's Global Positioning System, or GPS, is the most advanced and accurate navigation system available to seafarers. These satellites are high in orbit, thus allowing for several signals to be computed simultaneously by the receiver. The position accuracy is in the range of 100 meters. However, since the United States Department of Defense wishes to keep a strategic edge over other military nations, the civilian version of the GPS has an induced error factor called the selective availability, which at times can induce several hundred meters of position error. Sometimes too few satellites are available within the favourable angle over the horizon. In that case, an error called bad geometry or dilution of precision arises, and the calculated position may become unreliable. Depending on the receiver setting, it may decide to stop calculating the position entirely until the satellites are in a better geometry. The newer differential GPS system receives, in addition to the satellite signals, a correction factor from a land-based station. Its accuracy is to within a few meters. Without doubt, the radar is a highly important navigation aid. If it is aimed at collision avoidance, the radar is also good help in identifying coastline and buoyage in any weather conditions, day or night. Its range reading is more accurate than its bearing reading. However, a low-lying coastline with a long, flat beach will show up poorly on the radar. This is a potential hazard, as a radar may only show high features, far away inland, and give the impression that the coast is more distant than it is. The Raycon is a radar transponder, often installed on major waypoint sea marks. It is also often used on sea marks indicating the beginning or crossing of a traffic separation scheme. When activated by a radar signal, the Raycon sends it back with an identifier. It may be a short Morse code, such as the letter E, T, A or N. Digital charts, either presented on a plotter or an ecdys, have the advantage of being easier to read because information is organised in layers which can be displayed or hidden. Usually the digital chart will display the vessel's position from the GPS or a differential GPS receiver. Advanced ecdys technology can display the digital chart and the radar picture at the same time. Often the digital chart is overlaying the radar and the water area is kept transparent in order to show the moving targets and sea marks.